Okay, this is module 2 on work and energy. We're going to be talking about the conservation of energy and also the non-conservation of energy. So for energy to be conserved, the potential energy must be equal to the kinetic energy, so that the sum of kinetic energy and potential energy is equal to 0, and also the change in kinetic energy, which is the work done, and the change in potential energy must equal 0. So energy conservation, what we'd like to call the principle that energy can neither be created nor destroyed, is based on experiment. Even scientists discover new forms of energy. The conservation of energy has always been found to apply. So here we see a bicyclist starting at the bottom of the hill, and here he has kinetic energy as he's riding up, and actually the change in kinetic energy here. And when he reaches and he stops at the top of the hill, he now has potential energy caused by gravitation, and he will be going down the hill at a certain speed and reach a certain velocity down here. So down this slope, he'll be using kinetic energy. Going up, he'll be using kinetic energy. And so this is a perfect conservative situation where the kinetic energy plus the potential energy equals 0. Now that, of course, is leaving out any friction, air resistance, and any non-conservative work. So the conservation of energy is also equal to E, which stands for mechanical energy. So it's always what we call an isolated conservative system where E is mechanical energy. The work done is equal, as I said before, it's equal to the change in kinetic energy. In a conservative isolated system, E always must equal 0, where we can fill in the change in kinetic energy and the changes in potential energy and put the equations together and equate that to 0. Or in a conservative system, we can write it this way, where we have our final energy in these two terms here and equal to these two terms of the initial conditions. So our final conditions are here, our initial conditions are here. In a non-conservative or non-isolated system, okay, we have the change in kinetic energy plus the change in potential energy is equal to the work done in a non-conservative frame of reference. This is where the change in mechanical energy is not going to be equal to 0. It's going to be equal to some other integer other than 0. The change in mechanical energy states that energy is lost to either heat, sound, or transferred chemically. Okay, non-conservative systems of energy, isolated and non-isolated. So let's look at some isolated and non-isolated examples. Here we have work done that's non-conservative. We have kinetic energy here, and potential energy here, heat energy, sound waves, and radiation. So all these things can give non-conservative energy, okay? But these are all energy that could be in a system: kinetic, potential, thermal, sound waves, radiation. Where other energy is not immediately retrievable and is transformed to heat: mass transfer, sound waves, radiation. So this is always non-conservative. And so if we have friction, which we'll be working with mostly in Chapter 5, friction is something that does create heat and energy loss to the system that's not easily retrievable. So this change in mechanical energy is non-conservative. Also, the work done, which is a change in kinetic energy, just after reaching a constant V, then Ke equals 1/2 mv squared. So what that means basically is that if we look at the graph, we see that we're doing work. Then once we reach a constant velocity, then no longer we're doing any work. We're just using kinetic energy. So let's look at the conservative equation, and this is the long equation where we have the conditions, the final initial conditions for kinetic and potential energy, gravitational. We'll rearrange this to this equation right here, where we have the final conditions in these brackets minus the initial conditions of both potential and kinetic in between these brackets here. This is the energy conservation equation. So this is the equation that we'll use in problems to figure out what the energy is used, or the velocity, or the height, or even mass. Okay, so let's look at a problem. Find the kinetic and potential energy at 3 locations of the slope. So we have this slope, we have 3 masses, one situated at the very top, halfway down, and then C, which is at the bottom of the slope. Okay, and we get, we're told the distances that these blocks are away from the top. Okay, so we're going to use the conservation of energy equation. It hasn't said that there's any friction in here, so we're not going to worry about friction. There is a height. Back to using this equation right here. So this is the main equation we're using to find the velocity. All right, so then at each point we can find velocity A, B, and C. And basically the same thing using that equation. And we get, at the bottom, we get 55.2 meters per second. And potential energy now is 0. But kinetic energy is also 0. Because if we were to calculate it right at the point when it is 55, then we can say, okay, it does have 7,350 joules. But we're assuming in this right here, it stopped. Okay. Okay, so we have another problem. A 5 kilogram block rests on a 30-degree incline. When released, will travel 2.5 meters downward. Determine the work done by the force of gravity. And what is the work done by the frictional force between the block and the incline? So they're giving us right here a mu, and we're going to assume it's kinetic coefficient of friction of 0.436. And the mass is going to slide down the slope. Okay, remember from chapter 4 in dynamics, we have n equal to mg cosine 30 degrees. This is the angle right here, cosine 30 degrees. And then we have F perpendicular, which is exactly the opposite direction and equal to the same thing, only but opposite. And then we have the minus mg, which is the vector for the weight. Okay, and we want to find the work done also by number of force. So 3 things. Determine the work done by force of gravity. Okay, so the gravitational force acting on the object is equal to the weight equals mg. Okay, and so we get 49 newtons. Mass of 5, 9.8 meters per second squared. And the work done by this force is going to be the potential energy. And that's going to be equal to mg L sine 30 degrees. Now we do have the negative sign here because it will be going in that direction, downward. And downward on the slope is going to be negative in this direction. And so we have mg L sine 30 degrees. Just keep this in mind, the negatives, when you get to that point of putting the equations together. Then we have WG FL sine 30 degrees, and this is 61.3 joules right here. So this is the force times the length times sine 30 degrees. So basically all we did is that we have right here L sine 30 degrees, right here L sine 30 degrees. That is going to be the distance and times the force, and we get 61.3 joules. Okay, what is the work done by the frictional force between the block and the incline? So we want to find the work that's done. And actually the vector, the force vector, is going to be in this direction. So normal force is equal to N equals mg cosine 30 degrees. Frictional force is equal to umg cosine 30 degrees. Now you remember that mg equals N, and then we also have this angle here that we have to incorporate into the equation. Okay, work done by F. The work done is mu mg cosine 30 degrees times L, because we have to incorporate this L right here. And then let's plug everything in. We have our coefficient of friction, our mass, acceleration of gravity, the cosine of 30 degrees, and then 2.5 meters. And that is the distance right here. And we get 46.3 joules. Okay. And the work done by the normal force. Okay, well, the work done by the normal force is 0. Okay, it is perpendicular to the work being done, so it has no effect. Let's look at another problem. This has a 10 kilogram block, rests on a 45-degree incline. When released, will travel 5 meters. So determine the work done by the force of gravity. What is the work done by the frictional force between the block and the incline? And it gives you mu equal 0.256, and the work done by the normal force. Okay, so let's do this. The gravitational force acting on the object is equal to mg. So the force, that force mg, is equal to 98.0 newtons. A, and the work done by this force, since the potential energy is equal to the work done, positive. Okay, so we can say that the work is equal to this, and we can take the energy equation, and this is just delta H right here, YF minus YI, and we have this equation right here for the work done. Now, I'm sorry, not the work done. It actually is the work done, but it's actually also equal to the potential energy. And then we have F, L sine 45 degrees, 98 newtons. Okay, and that comes up here from the weight times the mass, or times the distance, 5 meters, and times 0.707, which is the sine of 45 degrees, 346 joules. Next one is B. What is the work done by the frictional force between the block and the incline? Okay, let's take a look at that. So equations used. Well, we have our normal force, and then we have our frictional force. Okay, so we need to know those equations. And you can go back to chapter 4 and look those up. Work done by friction is going to be equal to the work done is going to be equal to this force right here. This right here is the force times the distance, L. So the work done is going to be equal to this right here expression, and we multiply it out, and we get 88.7 joules. So this is the work done by friction. And the work done by the normal force, again, in this one is 0, because we have a slope and we have the normal force going up and F perpendicular going downward. Okay. Let's look at a different type of problem that is non-conservative. At a crash test facility, a 2,000 kilogram car is ran into a rigid barrier at a speed of 40 miles per hour. the car has a crumple zone of 1.25 meters, and for safety reasons in its design. So we have this car, and we have this crumple zone right here. Okay, and this crumple zone is going to change the distance. It's actually going to crumble up similar to this, and it's going to absorb energy when the car hits this rigid block. Okay, so find the energy lost due to the collision. Okay, so this is definitely non-conservative because the energy used to wreck the front end of this car cannot be used again so easily. So it's non-conservative. So we'll do this where MAD equals D, 1.25 is the crumple zone, okay? And we need to first convert 40 miles an hour to meters per second. And so for meters per second, it's equal to 17.9 meters per second. Plugging everything in, this v squared minus v squared naught divided by 2d, this is just the acceleration, okay? And if we plug in the values, we have an energy of 3.20 times 10 to the 5th joules, and that was all non-conservative work that caused the car to crumple up. What is the time that this happens in? So we want to find the time. So we have this equation right here, which actually these d's will cancel out. And actually they do not cancel out, sorry. This one cancels out, okay. We do have this one still, okay. And so we can plug in these values and we get negative 160 meters per second squared, which is a lot of acceleration. It's negative because it is decelerating. And then we can find the time if we have the acceleration and we have the velocity, we can find the time. And this happens all in 0.112 seconds. This next one is concerning a crate. We have a crate with 20 kilogram mass of bricks. It's pulled with a rope, 30 degrees horizontal with a force of 155 newtons and is moved 30 meters. Okay, the friction, so we have 30 degrees. The friction between the floor and the crate has a coefficient of 0.450. So 155, 20 gram mass. So let's take a look at this. The force acting on the crate is forward and upward. Only the forward force will be transferred into the work done. So remember these points here. We must pay attention to the normal force since it will factor into our frictional force of the system. The normal force is equal to the weight of the crate when in equilibrium. However, the crate has an external force, that's a rope pulling on it and moving along a frictional surface. The forces on the crate are not in equilibrium. The force factor will need to be factored into each individual component. Okay, so if you remember, we have a force factor like that. We have the x, and we have the y. Okay, so we have to factor those in to solve this problem. So the force on the x component will be the forward force times the distance. So we have this f of x right here. This is the only thing that's going to push this crate along the surface. Okay. The frictional force will be in the opposite direction. So we have our frictional force right here. For the frictional force, we must understand one thing. The y component of the force, which is acting as a lifting force, therefore making the weight of the crate less. So if we look over here, we have N and we have mg, but we also have this vector right here. This vector, F sine 30 degrees, that is coming from the y component of this vector right here. So this would be it right here. So this is the F, we can call this also Fy, as we can also call this one right here Fx. So F of y is affecting the weight of this crate. It's actually making it lighter. Okay, so we have a situation where we're going to have to incorporate that into the normal force. So we incorporate this in by taking the normal force minus the force times sine of theta. Remember, this is the vector that is going up, and it's making this lighter. So the horizontal force acting on a block without friction is this equation right here. In equilibrium, the normal force is always equal to the weight. Okay. What are the vertical forces on the block? So let's take a look at those. However, there is a second force acting in the vertical by a lifting effect. This will affect the frictional forces in the horizontal. So for frictional forces, we have F of y equals F sine 30 degrees, creating an upward force. Thus, our equation now that we're going to use for friction, we're going to use, this is our new, this right here, this part right here, the equation is our new normal. We can call that n sub nod. Okay. So our net work done, this is the work done by this part right here, by the forward motion on the x direction, force in the x direction, negative the friction, which is in the opposite direction, times this distance. What is the frictional force of the system? So let's start there and figure it out. Okay. Frictional forces is going to be equal to this equation. Just plug everything in and we get 53.3 newtons. Find the net work done. So they want to find the net work done on the pallet. So this is going to be the work done in the x. This is the work done right here on this vector, right there. Okay, that's the only forward work that's being done, forward force. And that's going to be equal to 4,027 joules. Okay, so next we already found the force of friction, 53.3 newtons. Now we need to find the work that it does, the non-conservative work. So this is non-conservative, 1599. Now we don't really need to put a negative sign there, but for the next step we probably will. To find the net force, and this is what is left that's actually dragging the box forward, is going to be equal to what we found in Wx, 4,027 joules minus 1599 joules. Okay, or we get roughly an answer of 2,430 joules. What is the energy loss to friction? Okay, well that's easy. We already figured out what the frictional force is, 53.3. We know that it's being applied for 30 meters, and so it is 1,599 joules. Okay, we're going to briefly talk about power, what power is. So far we've talked about power and different types of energy, kinetic, potential. Later on we'll get into potential in elastic systems. But let's talk a little bit about power. So what is power? Power is just simply the amount of energy that's being used per time. It's just a ratio. The work done over time. The units are always in watts. For example, the last problem, what was the power of the collision? Okay, with the car, we have the amount of joules of that collision, and it all happened in 0.112 seconds. And so the amount of power that collision produced was 2.86 times 10 to the 6 watts. So that is like over 2 million watts, and that is a lot of power. or we can write it as 2.86 megawatts. Also, if we take the equation, we can actually mix it around and try to get a force out of it, okay, where P power equals force times velocity. So this velocity, if we graph power versus force, okay, and we see where there is a force here and we have a certain power, we can find the velocity at that point. Now that is just a moment in time. So we can measure the exertion force too at certain instantaneous velocities.